we did this first problem here, where it's 2x plus 7y times 2x minus 7y, and we FOILed everything out. And at the end of the day, the important thing is that you know this formula here, that a minus b times a plus b is a squared minus b squared. Here we showed that when you FOIL things out, the middle terms cancel. And so we only have the first term survives and negative the square of the second term survives. So then the next example I wanted to do was 5x minus 4y squared. So here we're multiplying a polynomial to itself. And as always, the strategy is to distribute. So here, for example, there's many ways to do this. For example, I would take 5x and multiply to each of the terms here. And then once that's done, I would do the same thing with minus 4y. Take this and multiply to each of the terms here. And then you sort of use the properties of exponents. So when I do that, I get this. Here what happens is the middle terms actually repeat. Here, minus 4y times 5x, that's the same if I do 5x times minus 4y. So in this case, the middle terms repeat, and that's where this 2 is coming from. This is the value of the middle term, but we have it occurs twice. And so here, when we simplify everything, we get that's the answer. And at the end of this day, the moral of the story here is that this formula is very important. These two formulas are formulas we will use a lot. And so, I'm going to go ahead and use the M word. You should go ahead and memorize those, because these are formulas we can't even think about it. During the test, you shouldn't even take 1 second to go, how does that formula go? It should just happen. It should just immediately be at your fingertips, okay? This is the discipline of math, you know what I mean? This is just how it is. This is what we do. I had this third example here, which is actually very sneaky and tricky. So the nature of the example is trying to not trick us, but really, one thing we might be tempted to do is FOIL this out, expand that out, and then expand out the second term, and then expand out, multiply the whole mess together. And certainly we can do that. That would not be incorrect. But to me, that's the long way around. There's a much shorter way to solve this problem if we're a little crafty. So here what I want to do is use this property of exponents right here. And I want to pull out the exponent. Specifically, this square term here, I've pulled out completely. If you do that, that makes the problem a lot easier. Now we have to do this multiplication on the inside, which is basically looks like this. If you look, it's a plus b times a minus b. So if I use the shortcut formula for that, that's a squared minus b squared. And then don't forget we had the square on the outside. This original square that we took out is still there. That's the original square. So square root x squared minus square root y squared, that just looks like x minus y squared. So now we can use this formula to FOIL it out. It's x minus y squared. So when we use that formula, we get our final answer here. So none of this stuff is particularly difficult, but these are these fundamental mathematical steps that we will do over and over again. We're constantly FOILing, we're constantly doing properties of exponents. So it's important that we know these rock solid, because this is where the mistakes are going to happen. The things we do the most often, there's probably a good chance we could, if you make a mistake there, it causes problems. So the other thing I want to talk about is simplifying. And that typically causes some issues. So here I say simplify the rational expression. Remember, a rational expression is basically a fraction. And so here we have 3 different problems. So for this first problem, how are we simplifying? When we say simplify, so there's a typo here. I'm missing the letter L, simplify. I'll correct that. So for the, when we say simplify, we're basically looking to do 2 things. One is to factor out any common terms. And 2, if you have a fraction, is to cancel any terms. So for this first problem, I'm looking at the top numerator and denominator. Certainly in the denominator, there's a common term I can factor. So here, I'm going to try and factor. So in the denominator, you can factor out an r squared. And in the numerator, you can actually, if you do reverse foiling, you can actually factor it as 3 plus r times 4 minus r. And so, you know, right now, I want you to think about, okay, I want you to remind yourself of how you do reverse foiling, whatever your technique is, because they've taught many different techniques over the generations. You know, one thing I'll do here is just to check 3 times 4 is 12. Plus r times minus r is minus r squared. And the middle term, you have 4 times r is 4r times minus 3r is just r. So that is the correct factoring. In the denominator, there's a common term, namely r squared. R squared is common, so I'm factoring out r squared. Just to remind you, when we factor out something, what that means is we're dividing every term by the term we're factoring out. So here, when I factor out r squared, I have to divide r cubed by r squared, and I have to divide 3r squared by r squared. And so I can simplify the denominator this way. So we've factored out common terms. The other thing we try to do in simplifying is to cancel. And here, 3 plus r and r plus 3 are the same term. So we can cancel in the numerator and denominator. So this is my simplified answer, 4 minus r over r squared. And I say provided r is not equal to 0 or 3. So that's the domain restriction. It's very important that we realize there's a denominator here. And none of this math, all of this math that we did, none of it will make any sense if r equals 0 or if r equals 3. If r equals 0 or if r equals 3, then this expression is undefined. So that's why I've kind of just made, you know, pointed out here that r can't be -3 or 0, because those are the roots of the denominator here. For the next problem, it's kind of opposite. Here, we have to put the fractions together. We have to combine them. Here, it's really important that you notice there's an operation in between the two expressions. There's a subtraction. And there's a subtraction of fractions here that can still be done. So how does this work? You remember how to work with fractions? I need to have them both over a common denominator. So I'm multiplying the first fraction by 3s plus 1 over 3s plus 1. So I can get this common denominator of 3s plus 1 squared. Once we have the common denominator, then we can combine the fractions. So I've got the common denominator here. And so here's my first numerator, 4 times 3s plus 1. That appears right here. And then the other term that we have to contend with from the second fraction is a minus 11. Minus 11. And you see that occurs right here. And so now, just some basic algebra, right? I'm going to distribute the 4 to each term. So 4 times 3s, 4 times 1, so that's 12s plus 4, minus the 11, 4 minus 11 is -7. So here's my simplified answer at the end there. Don't I multiply by the same thing but with a different sign? I'm not sure what you mean, Nick. So I'll let you. Go ahead.
Sorry, can I just quickly interrupt you? When you multiply by 3s plus 1, don't you? I thought you multiplied by 3s minus 1 on the denominator and numerator.
So what we do downstairs, we must do the same thing upstairs. So if I multiply in the denominator by 3s plus 1, I have to multiply in the numerator by 3s plus 1 also.
Okay, yeah, I just heard that you multiply with a different sign. Maybe it's just a different thing I heard. But...
Well, you might be thinking of this formula here. So I just talked about this formula. So, you know, you might be thinking of that. But,
okay.
But in this scenario, what we're trying to go for is we want both fractions to have this as its denominator.
Oh, okay. Oh, yeah, that makes sense. Yeah. So
Yeah,
yeah,
and
I
so
feel
here I'm multiplying, and remember when I do the bottom, I got to do the top. So there's my,
Yeah,
they
yeah.
call it a convenient one.
Yeah, sorry, my mistake. Thank
No,
you.
no worries. You're good. You're good. Thank you for your question. So for the third problem, to me, this is again, the third problem I put here is a little bit sneaky and tricky problem. And I think it's very important that we stop and really take some time to see what we're looking at. And so for me right away, I think it's very important to realize, oh, when you say y to the -1 and x to the -1, x times y to the -1, these are all fractions. And I really think it's important to rewrite this, at least for me, to think about this conceptually, to really think, these squiggles, we should always think about what do they really mean? We should come back to what's the true meaning here. So here, what we have is a fraction of fractions. And we don't want that. I never want fractions in my numerator of my fraction. So here, right away, I need to simplify this expression upstairs, because I don't want a fraction in the numerator of my fraction. And I need to do something about this expression downstairs as well. Again, I don't want a fraction inside my fraction. For the numerator term, what we'll first do is combine the fractions. So for 1 over y, I'm going to multiply top and bottom by x. So here I'm going to do x over x. For 1 over x, I'm going to do y over y. And then I can combine the numerator into a single fraction. And then finally here, there's this definition. Let me go forward here. Let me show you. I want to use this definition here, finally, to get rid of the 1 over x1. So if you look at this, a divided by b is the same as a times the reciprocal of b. Okay? So here in the denominator, this term that I'm referring to as b, you should think of the entire 1 over xy as b. And here, this term in the numerator here, this term a that I'm referring to, think of this entire thing in the numerator as a. So now I'm going to do a times 1 over b. This right here is the reciprocal, right? So right here, this is the reciprocal of b. 1 over b, this is the reciprocal of b. The reciprocal of 1 over xy is just xy. So here I've just done the definition. A times the reciprocal of the denominator. This is the reciprocal of the denominator. As you can see, there's this common term, xy, which will cancel. This cancels, this cancels. So my final answer is x plus y, but I really need to write this part. Even though x plus y is defined for x and y equal to 0, these fractions are not. And the only way any of this math makes sense, the only way any of this, the only way any of this makes sense here is if starting out, we know x and y are not equal to 0. Because if x and y are 0, this fraction right here breaks down. This will not be defined. All right, gang, basic algebra stuff, but I want you to review this, make sure it makes sense to you. It's always makes sense and easy when you have the answer in front of you. If you don't have the answer in front of you, it's a whole different ballgame. And that's what you're training and planning for, when you don't have the answer in front of you. The other thing I see a lot of problems is in simplifying the expression. So here we've got this sort of complicated expression. This is a little more complicated than what you might see in a test, but not necessarily. It's really not that bad. It just looks kind of bad. So here, when I say simplifying, what do we mean? We want to combine any terms we can. We want to factor out any common terms. We want to cancel anything if there's numerator and denominator, okay? So here's starting out. When I look at this thing, and I've trained myself for years and years of teaching math. I've just trained myself to look for certain things. So here, right away, I notice there are terms first that I can combine. 2 times 4 can be combined. the 1/3 and the 3 can be combined. So let me first combine terms. So here when I multiply, the 2 times 4 becomes an 8 right here. And 3 times 1/3 is just 1. So that just disappears if you wish. Or, you know, whatever. Here's a 1 if you want. 3 times 1/3 is just 1. So now after simplifying, now let's take a look. So now we want to just look at this thing and ignore the previous line. We're done with the previous line. So now I'm looking for common terms. So the common terms I'm seeing, you know, 3x plus 2 occurs twice. And 4x minus 5 is a common term. So here you have two options. You can try and factor out the lowest power of the common term. In this case, because I have a fraction, I'm actually going to combine the fractions. So here you should see there's a plus symbol here and there's two terms. This second term is a fraction with a denominator. So let me make the first term have the same denominator and let me combine the fractions. It's really important you see the plus sign there and that we have a fraction as our second term. So there's this addition we can do. So what I do is I multiply the first term, top and bottom, by 3x plus 2 raised to the 2/3. And here, don't get disoriented. Here's that plus symbol. Here's the sum that we're eventually gonna, you know, want to do. So now when we do the multiplication, if you look, these two terms have the same base. 3x plus 2 to the 2/3, 3x plus 2 to the 1/3. Since the bases are the same, we can add the exponents. And so we can combine those terms and then combine the fractions. So here, this is what we get from the first fraction. Remember, here's that plus sign. We've finally done the addition of the two fractions. And here's our second fraction is you know, giving us this 4x minus 5 squared. So there's everything combined. Again, I'm looking again, can I factor out any common terms? Can I combine any terms? Can I simplify anything? So again, now we ignore the previous step. So now at this stage, we're now just looking at this and ignoring the previous stage. And here again, I see common terms. I'm sure you see 4x minus 5 is common. So the rule is you factor out the lowest power of the common term. So here I want to factor out 4x minus 5 to the first power. This is the common term to the lowest power. Here 4x minus 5, this is squared. This is to the first power. So factor out 4x minus 5. So this term here disappears completely. This 4x minus 5 I pulled out completely. Here when we factor out the 4x minus 5, this goes from being squared to power 1. When you factor out. Remember, you're dividing each term by 4x minus 5. That's what we mean when we're factoring. So finally, let's clean it up. 8 times 3 is 24. 8 times 2 is 16. So sorry, 8 times 3x here is 24x plus 4x is 28x. 8 times 2 is 16 minus 5 is 11. I should have 28x plus 11 in that parentheses there. So that's our final simplified form after factoring out all the common terms and combining. Again, this is basic algebra, but we do this a lot, and mistakes here are going to trickle down and cause a nightmare for you. Okay? When we're doing a derivative, sometimes when we do a quotient rule, we need to simplify the quotient. And if you don't simplify it properly, that can cause problems. So the math isn't hard, but you should review each of the steps and make sure you understand how to do it. And you know, practice always makes perfect. At this stage, it's about practice and working super hard. Everybody's smart. I got another irritating simplify the expression problem. Did I spell simplify correct at least this time? Yes. So here, again, what are we looking to do? We're looking to combine any terms, factor out any common terms, or cancel out anything. Okay, so the first thing I notice here is there's some math we can do. So first of all, we can go ahead and square down here. We can multiply these two exponents. And then what else can we do? Let's see. I can multiply the 8x and the 1/2 in the numerator. Okay, so right off the bat, let me first do the basic simplification. Multiply the 8x and the 1/2 and square the denominator here. This 1/2 and the two properties of exponents, we can just multiply those. So when we do that, it looks like this. Now reset. Ignore the previous line. Now we're just kind of starting from here. And what am I looking for? Common terms, anything I can combine or anything I can cancel. Here, there's nothing that we can combine. There are common terms. So here, I've got a 4, and here I've got a 2. So obviously, they have 2 in common. Here also, we have a 4x squared plus 9 to the 1/2 and a 4x squared plus 9 to the minus 1/2. So the rule is we're going to factor out the lowest power of the common term. So here I'm going to factor out a 2 and 4x squared plus 9 to the minus 1/2. And remember, when you're factoring out, what that means is you're dividing. So here, each of the terms, when I factor out, gets divided by that thing that I'm factoring out. So this numerator term here is right here. And we're dividing it by the thing we're factoring out. And this second term here is right here. And again, we're dividing it by the thing we're factoring out. And so now, again, we're doing basic algebra now. The 2's cancel. There's a 2 here and a 2 here. This minus 1/2, it goes up because it's in the denominator with a negative exponent, so it actually should be in the numerator. So in the numerator, I get 4x squared plus 9 to the 1/2 times 4x squared plus 9 to the 1/2. That's going to be 4x squared plus 9. Over here with the second term, we can cancel the 4x squared plus 9 to the minus 1/2 completely because it appears in the numerator and denominator. And then this 4, I can cancel the 4 with the 2 down here and replace that 4 with a 2. So the second term should be 2x times 2x plus 3, which is exactly what we have. So now, we forget about the previous step, and now we're just focusing on this. And again, I'm asking, is there any cancellation I can do? Are there any common terms? So the only thing left to do here is this term, because it has a negative exponent, can be moved downstairs. And then here, these terms in the square bracket here, these now just need to be combined. So here, minus 2x times 2x is a minus 4x squared. So here you have 4x squared minus 4x squared, those cancel. I have a 9, and then this minus 2x distributes to the 3. So remember this minus 2 here, this minus 2x, I'm going to multiply. And so when you multiply and do the cancellation, that's what it looks like. The 4x squareds canceled. We're just left with a 9 minus 6x. Finally, there's one final simplification to do here. 6 and 9 both have 3 as a common term. 9 is 3 times 3, 6 is 3 times 2. So I factor out a 3, multiply it to the 2 that's hanging around outside. And this is our simplified form of this horrible mess. So this is all algebra. It's not hard, but it's not easy either. I can see a bunch of places here where anyone could make a bunch of mistakes. And I think, the trick for me, at least the first couple of times, is to not skip too many steps. When I skip steps, that's when I make mistakes. So the last problem here is basically now we're given an equation. Okay, I want you to think about this. Every problem before was not an equation. It was just a term by itself. Now we have a left-hand side and a right-hand side. So we have to keep track of both sides. So this problem I put because, one very common mistake that's very natural that a student might make is from this equation, I could see a student saying, Well, we can just take the reciprocal of both sides and we can write f equals p plus q. Problem is that's not true at all. Problem is this is completely false. So hold on. This is totally wrong. So that's the main trap here I would want you to not fall into. Let me just take the reciprocal of everything. What we should notice is that on the left-hand side here, there's math that can be done. These two fractions can be combined into a single fraction. I'm going to multiply the first fraction top and bottom by q, the second fraction top and bottom by p, and then we can combine them. Now, if you want, you can take the reciprocal of both sides. Now you can flip them both over because you have a single fraction on one side and a single fraction on the other. Flipping them doesn't help. Here, the next step, what does help is cross multiplying. So I'm going to take the PQ and put it on this side. And here, draw parentheses around Q plus P and take this F and multiply it to the other side. We're going to cross multiply. So cross multiplying gives us PQ equals F times P plus Q. And remember, we're trying to solve for Q. So I want to isolate Q. I want to collect all terms that have Q in them. So now I'm going to distribute the F and then move anything that has a Q attached to it. So here's a FQ. I'm going to move this FQ to the other side with the PQ. I want everything that has a Q in it to be together. And so when I move that FQ over, I get PQ minus FQ equals FP. And now I can factor out the Q and isolate it and solve for it. Factor out the Q on the left-hand side here. Divide both sides by P minus F. Of course, I make the assumption here that P minus F is not equal to 0. Actually, I make the assumption that F, P, and Q are all not equal to 0, and P minus F is not equal to 0 for this problem to make sense. So this was the review of the first day. It was a little trickier. The problems are slightly harder, but I wanted to do that on purpose. I don't, I'd rather give you harder problems and then you see slightly easier things on the test. Okay, so let me fire up the lecture for section 1.1, which I sent you in an email yesterday. And so I'm slightly behind, but not really that behind. I'll be caught up by tomorrow. So section 1.1 and 1.2 is all stuff you've done before in pre-calculus, in algebra. Okay, so here we're going to introduce the concept of a function. You know what a function is, but we're going to introduce some new terms and maybe some new notation, okay, which we'll use throughout the class. So the first new term, which you may or may not have heard, is the term a set. So a set is a collection of objects. And so we use these curly brackets to indicate that we have a set. Here I have a set of 3 dots. It's not a very interesting set. So for example, the set of non-negative integers. So pay attention to all those words. Non-negative, that means we can include 0. So positive means bigger than 0. So here non-negative means greater than or equal to 0. Integers, so these are numbers that don't have any decimals and no fractions. So the set of non-negative integers is denoted as, so here's my curly bracket to indicate I have a set. And so once I see that curly bracket, I go, aha, this is the set containing the numbers 0, 1, 2, ... or the set of integers. Here, let's define our own set. So this notation, if I say S equals curly bracket Larry, Mo, and Curly, I would read this, in math, we would read this as a sentence. We would say S is, so in a set definition like this, you interpret the equal symbol as the word is. S is, when I see this curly bracket, I know it's a set. So I say S is the set containing the words Larry, Mo, and Curly, or S is the set denoting the 3 Stooges. Larry, Mo, and Curly are said to be elements of this set. You see Larry appearing in the set S, Mo appearing in set S, and Curly are said to be elements of the set S. A set is is made up of objects. Each of these objects are called elements of the set. So the set of real numbers, which we use in calculus, so that's one big thing about calculus, is we don't do math with integers. All of our math is over real numbers, okay? And that's something we'll talk about in another day, but that's one fundamental importance of calculus, is that we're doing math over real numbers. So the set of real numbers is denoted with this fancy R. And if X is a real number, so this sentence in English, we would write in math this way. And this symbol that looks like the letter E, that stands for element of. So we would read this as X is an element of the set of real numbers, or X is a real number. And we will use this notation. You'll get used to it the more we use it. But if you see X, Euro symbol looking thing, fancy R, that's just me saying X is a real number, okay? It's, you know, this will come up a lot when you're in Calc 2 and Calc 3 and differential equations and matrix methods, you know what I mean? So it's important that you see it now. So let's define a function. A function is basically a relationship between two sets. You have a domain and codomain. So typically the word codomain is not used as much in algebra or pre-calculus, but it comes up later. A more common word that's used is the word range. So the domain is the set of all possible inputs, and the range is the set of all possible outputs of the function. The function is thought of as an input-output machine. You give me an input, the function will spit out an output. The input has to come from the domain. And the set of all possible outputs, that's called the range. So let me do an example here, a really cheesy example. So here I define a function again. I say it's a rule, you know, a rule or a recipe that assigns each element X in the domain, we assign to it an element Y in the range. Okay, so let me do a quick example here using S as our range space or target space. So here, let me define the domain D to be the set containing the numbers 1, 2, 3. So you should read this sentence as D is the set containing the numbers 1, 2, 3. And now I'm defining my function. F of 1 I define to be Larry. F of 2 I define to be Mo. And F of 3 I define to be Curly. So then here what we have is a function from the domain D to S, and we write it this way. We write the notation this way. So given any element in D, like 1, 2, or 3, the function F will spit out an output like Larry, Mo, or Curly. So here, F is the function, D is the domain, S is the range. What's the codomain? Here, the codomain would be Larry, Mo, Curly, or Shemp. So for those of you who don't know, there's actually 4 Three Stooges, right? So listen to this sentence. There are 2 sets of 3 Stooges that comprise of 4 people. So originally the 3 Stooges were Larry, Mo, and Shemp. And then it was Larry, Mo, and Curly. So part of calculus is to figure out, are you a Shemp person or a Curly person? I'll let you worry about that. So here, the codomain is a set where the range can live in. Okay, so don't worry about codomain so much. It'll come up in a couple of years, in a couple of semesters. And I just want you to see that word now. But don't worry about it. In calculus, it's just domain and range. By the way, I can break the function. If I define f of 1 to be Larry, f of 2 to be Mo, f of 3 to be Curly, and f of 1 to be Shemp, this breaks the function. Here now, I no longer have a unique output for the input 1. Here, 1 is associated to the output Larry, but 1 is also associated to the output Shemp. And so this violates the uniqueness. Here, for any one input, I can only have 1 output. So 1 either gets outputted to Larry or 1 gets outputted to Shemp. 1 cannot be sent to both Larry and Shemp. So here's kind of a visualization. We think of a function as kind of this box, and you give me an input, X, and then the function spits out an output. What we don't want is the function to spit out 2 outputs. Then it's not a function. Another way to visualize is we visualize the domain as being this blob with points. And here the range is this blob, and you have the domain points are being sent to the points in the range. Now look, if there was a point that was not being mapped to, if there's a point here that's just by itself that is not being mapped to, then E would actually be the codomain. And in this case, if there's a point that's not being, sent to by the function, in this case, only these points here would make up the range. Okay, and E would be the codomain. But here, E is the range because everything in E is being mapped to. Here, what we don't allow is for A to go to another output. We can't have A going to two different outputs. That's not allowed. So here, in calculus, the way we do our functions is we have the x-axis and the y-axis. The x-axis measures your horizontal distance, positive or negative from the center, the origin, and your y-axis measures your vertical distance, either positive or negative from the origin. For any input, for example, 1, we plot the corresponding y value above or below that input. So for 2, I have f of 2. For x, I have f of x. And we can create what's called a graph. And so here you can see in this graph here, this part is the domain, set of all possible inputs. This part here is the range, set of all possible outputs. And the entire y-axis here would be our codomain. It's where the range lives, okay? But don't worry about codomain so much. In this class, domain is extremely important and range is important. Domain is like super important. And we'll talk about that a lot. I'm a mathematician, so I'm obsessed with these things. So here's the official math definition for a function. And it looks a bit mysterious, but if we decode it slowly, it kind of makes sense. So here's what we're looking at. So it says a function y equals to f of x is a well-defined function if and only if, and here's the rule that we want to look at here. x1 equal to x2 implies f of x1 equal to f of x2. So well, what the heck does that mean? What this is saying is if you're starting with two inputs and they're the same, so I have input x1 and x2 and they happen to be the same, then when I put it into the function, I better well get the same output. So starting with two inputs that are same, x1 and x2, when I put it in the function, I get f of x1 as the output for the input x1. I get f of x2 as the output for the input x2. But since the inputs are the same, the outputs better be the same also. And that's what this definition says. If you're starting out with two inputs that are the same, then their outputs have to be the same. The x variable is called the independent variable. The y variable is called the dependent variable. A visual definition, the visual interpretation of this definition in the red box is known as the vertical line test. Basically, what we're saying is that any vertical line can only intersect the graph of a function once or 0 times. So if any vertical line intersects the graph at most once, what do I mean at most once? Either once or not at all, then the function will be a function of x. If any vertical line intersects the graph of f of x more than once, then f of x is not well defined. It's not a function of x. And look what happens here. I drew a picture here. So look at this graph here, where it's failing the vertical line test. We get a mathematical contradiction, which is bad. Look here, for the input A, we have output B. So we know f of A equals f of B. But look, for the input A, we also have this output C. So here I know f of A equals f of C. But B and C, in this particular case, B and C are not equal if you look at the graph. B and C, however, are not equal. So now if you put the ends of the equation together, we get this ludicrous statement that f of A does not equal f of A. This right here in math is known as a contradiction. And when we get a contradiction in math, that's bad. And so this is the reason we require the outputs for any function, for any input, to be unique. We can't have one input going to two outputs. If we do that, well, then we can basically manufacture a contradiction. We can get a statement that's a false statement. And above all, in math, we want to deal with true statements. So this is the reason we need the inputs to be unique. Otherwise, we can get a contradiction. And the simple way to visually see if you have a function or not is called the vertical line test. This determines if it's a function of x. We can talk about what it would mean to be a function of y also, we can do that next time maybe. So here I just want to show you a graph of some common functions. These are all shapes you should recognize, and we'll actually talk about these more in depth next time. So the book actually starts doing graphing in section 1.2, but I thought it was important for you to go ahead just to remind you to see these common shapes that you know and love, just to see them right now. Because we're going to use this a lot, and the more we can look at this, the better it'll get. And I'll go through each of these next time, okay? One very important type of function I want to talk about is called a piecewise defined function. And so here, if we define a function f of x using two or more different other functions, then that's known as a piecewise defined function. Basically, we're using functions and we're doing sampling, like they do in the hip and the hop. We're sampling different functions to create a new function, right? So here, take a look at this example here. Here, this function that's given to us is a piecewise defined function. So what I want you to focus on, ignore everything, just focus on this. And here, when you look at a function that's defined like this, the most important thing I want you to realize is this part right here is the domain. And for this particular piecewise defined function, we've broken up the domain into three pieces. Here's the first piece, x less than 0. Here's the second piece, x between 0 and 3. And here's the third piece, x greater than 3. And in each of these pieces, we've got a different definition for the function. If x is less than 0, then we define the function to be x. If x is between 0 and 3, we define the output to be 3. If the input is x greater than 3, if the input is to the right of 3, we define the output to be negative x. So this is how we can graph it, by just graphing the appropriate function in each piece. So here we have our three pieces. And so in this section here, I want to graph y equals x. In this section here, between 0 and 3, I want to graph y equals 3, the constant function. And in this section here, I want to graph y equals negative x. And so that's what I've done here. You can see right here, this section, this first section, x less than 0, this is the graph of y equal to x. But I don't want the entire graph. I just want the portion of it that's, in this section, x less than 0. And here, this portion you can see is exactly the graph of y equal to 3 for this middle section, middle piece. And finally, you can see for this third piece here, this is exactly the graph of y equal to negative x. This is exactly the graph of y equal to negative x. But I don't want the entire graph. I just want that portion of negative x from 3 onwards. And so I think it's really important for you, to get comfortable with these types of piecewise defined functions. And most important is to realize this is specifying the domain. It's breaking up your domain. And this tells you what the function should look like in each piece. Okay, so these piecewise defined functions are functions that can look weird and that we can make it look weird because we can put together a bunch of weird functions. Just the notation, just this notation can sometimes mess with people. Just this mess right here can mess with, when your eyeballs get a little freaked out, like what's going on? What's with all the brackets and blah, blah. Okay, so think about dividing the domain into pieces and then graphing each piece, okay? So the most famous piecewise defined function, and I'll just finish up this last slide and stop here. And then there's only 2 more slides left to finish up 1.1, which I'll definitely do tomorrow, okay? So you can either try to do the WebAssign yourself, or you can wait until after tomorrow's lecture, because the WebAssign will be due at 5 p.m. tomorrow, not tomorrow, on Friday, excuse me. It'll be due at 5 p.m. So you'll still have plenty of time for me to lecture about it before the WebAssign. Anywho, the most famous piecewise defined function. Famous, Sajid? Yes, famous. is known as the absolute value function, okay? I can't stress enough, here we're introducing this new notation. It's 2 vertical bars with the X in between. I can't stress enough how much our brain doesn't really understand 2 vertical bars, okay? So here it's really important when working with the absolute value to always think about its definition. The way we decode this notation, instead of working with the 2 vertical bars, we rewrite it, we decode the notation using its definition. And here, if X is greater than or equal to 0, it's equal to X. So you can see the graph here. And if X is less than 0, it's equal to negative X. So that's how we've sketched the graph, accordingly, just each piece. Okay. So some fun facts about the absolute value. For any real number, the absolute value of that real number is greater than or equal to 0. It's non-negative. Any number or its negative is less than or equal to its own absolute value. For any 2 numbers, A and B, we can do a geometric interpretation of the absolute value of A minus B or the absolute value of B minus A. That can be interpreted as the distance between the points. And here we have a very famous inequality. You don't really need to know it that much for this class. They used to teach it a lot in pre-calculus, and I don't know if they do anymore, but it's a very famous inequality known as the triangle inequality. And I'll just show it to you this once, and just so that you have it in your brain. It says the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. This is a really important inequality in mathematics, and it'll come up a lot later in your career. So I just want to mention it now. Like I said, they used to teach it in pre-calculus back in the day, but I don't know if they still do. So here's some quick applications here. For example, the absolute value of -2. I want you to think about how we're using the function. So here, I'm looking at -2. -2 is the squiggle. And I'm asking the question, like a computer, is the squiggle in between less than 0 or greater than 0? In this case, it's less than 0. So the definition of absolute value now says, okay, just copy down the squiggle in between the vertical bars, but slap on a minus sign in front of it. So look here, if we just follow the definition, absolute value of -2, note the squiggle in between the vertical bars is less than 0. So by definition, I just copy down the thing that's in between the vertical bars and slap on a minus in front of it. And then of course we know -2 equals 2. So we can do that final simplification. Geometrically, what can we conclude? Well, we can say, well, this tells us the distance between -2 and 0 is 2 units of distance, if you want to do a geometric interpretation. For example, absolute value of pi. Again, I want you to think about like a computer. How does this work? So the symbol between the squiggle is pi. So now I ask the question, is this greater than or equal to 0 or less than 0? Well, it's greater than or equal to 0. So the definition says, if the squiggles in between the vertical bars is greater than 0, just spew back out the same squiggle. So here, pi is greater than 0, so absolute value of pi, I just spew back out the same squiggle. Absolute value of pi is pi. Finally, of course, absolute value of 0 is 0. I mean, there's no of course about it. It's by definition. That's just how it's defined to be. All right, gang, I'm going to stop here. It's exact.